Hello and welcome to this video on the ICND1 series. In this video, we're going to look at IP version 6. So we're going to be looking at what IP version 6 is. We're also going to be looking at the kind of IP version 6 addressing. We're also going to look at how IP version 6 addressing is actually represented. And we're going to look at technologies that can help us transition from IP version 4 to IP version 6. So first, why do we have IP version 6? IP version 6 was designed as a protocol to replace IP version 4. And the real reason why IP version 6 was designed, because we're running out of IP version 4 addresses. Now, if you remember, IP version 4 addresses had 32-bit, and because they had 32 bits, there are just about 4 billion addresses that were available, and we have way more than 4 billion devices in the world. And when you start looking at computers and phones and tablets and watches and all kinds of devices now that have IP addresses, we can see the reason why IP version 4 addresses have been exhausted. But so far we still use IP version 4, and the reason is because we have network address translation. And what NAT does is that it translates private IP addresses to public IP addresses, and with NAT you can translate about 65,536 IP addresses to a single public IP address. So it really helps us to conserve IP addresses. But the problem with that is that NAT normally breaks stuff. You have things like authentication, or basically any scenario that you're supposed to have a clear IP channel. Once you have NAT translation, it happens in between. Most of the time, it breaks a lot of technologies. And if you've been in networking long enough, you realize that NAT is as bad as as good. So most people will prefer to have global IP addresses. And so a lot of people have been canvassing for IP version 6 deployment. But the problem is it's really hard to create a case for IP version 6 deployment from the business side, because a lot of investment has gone into IP version 4. And so business owners don't just really see the need to migrate to IP version 6. I think the real time we're going to migrate to IP version 6 finally is when IP version 4 doesn't work anymore. It's when we just totally run out of IP version 4 address space. There's no way we can work with IP version 6, and people will be forced to migrate. So aside from the fact that IP version 6 is a lot larger, like you have 340, I think it's called undecillion number of IP version 6 addresses, it's just almost impossible to exhaust them. So with IP version 6, you can have all the devices in the world to have their own global IP version 6 address, and we still have a lot of IP addresses that are still unused. Another reason why IP version 6 is better, because it has a simple header. But when I say it has a simple header, I don't mean that it has a smaller header, but it has less options. So with IP version 4, either you can have something like this that has all the flags here and flags here are different options, and the router has to process all these options. But with IP version 6 address, you have with IP version 6 addressing, you have way less options. So it's actually easier for the router to process IP version 6 packets because it has a simpler header. Another reason why IP version 6 is preferred to IP version 4 is that IP version 6 is more secure in the sense that when IP version 6 was designed, it was designed to be a protocol that runs with IPsec. So it has the security encryption with IP version 6 by default. So we have two IP version 6 devices communicating with each other. Packet 2 being encrypted and is a lot more secure than IP version 4. Now, let's move on to IP version 6 addressing. So we already know that IP version 6 addresses are 128 bits long. Now, for IP version 4, we express them in dotted decimal. But in IP version 6, they're expressed in what's called hextets. And hextets are hexadecimal octets in a way. So one hextet has 4 hexadecimal numbers. And what's a hexadecimal number? Hexadecimal number is a number in base 16. And what that means is that it's a way of expressing numbers with 16 digits. So you have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and that's 10 numbers. You also have A, B, C, D, E, F. So that's 16 numbers. So pretty much what this means is that A represents like 10, 11, 12, 13, 14, 15. So the hexadecimal notation has 16 numbers. Now, when you have a hexadecimal number, so if we pick any hexadecimal number, for instance, if we pick D, for instance, D is 13. And you can express it in binary. If you convert 13 to binary using our holders, we have 8421. So 13 would be 1101. 8 plus 4 equals 12 plus 1, 13. So that's 1101. That means that you need 4 binary numbers to represent one hexadecimal number. So you can go from 0 to F, and that would be 0000 to 1111, which is F. So for every time you write a binary number, you can represent 4 hexadecimal numbers. So when you have 128 bits binary numbers, you can represent them using 32 hexadecimal numbers. So if you want to represent an IP version 6 address, what you're going to have a number like 2ABD, and then you have a colon. You can have 1111 dot colon 0023 colon 0000 colon 0000 colon 0300 colon. This is 1, 2, 3, 4, 5, 6. So if 2 octets to go, 1DFF colon 2ABC. Now this is an IP version 6 address, and it's that long. So there are ways to reduce the IP version 6 address if you have strings of zeros. So for instance, if you have 0000 and 0000, you can replace them with 2 semicolons. So for instance, you could reduce this address to 2ABD colon 1111 0023 colon, and just put another colon for these 2 strings. So even if you have 3 hex sets and have all zeros, you have 0000, 000, and then you have another 0000. You still represent all the zeros with 2 colons, and then you continue. So let's have 0300, 1DFF, 2ABC. Now what happens if you have like 0000 and they're more than one position? So for instance, if we have this as 0000, and then there's another string of zeros on the other end, you can only use this double semicolon once. So you can have an address that is 2ABC double semicolon 1, 2, 3, 4, and then another does double semicolon ABF8. The reason why you can have this is that the router or the device will not be able to expand this. So it doesn't know how many zeros to put here because it knows they're supposed to have 8 of those hextets, but it doesn't know how many of them are here or how many are here. So you can only use the double colons once, and the rest of them you can express as zeros. Another thing you should know is that you can represent another way to reduce it is to remove all the leading zeros. So when you have something like 0023, you can just make it 23, or 0300, you can make it 300. But of course, you cannot remove the trailing zeros, so you can't say 300 would be 3. That wouldn't be right. But you can remove all the leading zeros. So you can have this to be further reduced to 2ABD colon 1111 colon 23 semicolon 00. You have double colon here, 1DFF and 2ABC. So that's one way to represent it. I would encourage you to take some time out to practice IP version 6 addressing. Know how to reduce the expression of IP version 6 addresses, because it's likely that you can get questions on those in the exam. Now let's move on to types of IP version 6 addresses. So the way we had types of IPv4 addresses, when we had public addresses and private addresses, we also have kinds of IP version 6 addresses. Remember how we had unicast, multicast, and broadcast in IP version 4? Now we have just unicast and multicast. So broadcast has gone. What it really means is that broadcast has been swallowed up in multicast, in the sense that multicast is one too many. So you can have a multicast address that everybody is a part of, and that becomes a broadcast address. But the concept of a broadcast address separate from a multicast address has been taken away in IP version 6, and that kind of makes sense. So the way to recognize a multicast address in IP version 6 is that it starts with FF. Now it could be FF anything, but it starts with FF, and you know that that's a multicast address. Now there are different kinds of unicast addresses. The first one is the global unicast address. And the global unicast address is just like whoever have asked the public IP address in IP version 4. And this is the addresses that the router and the internet, and the range is 2000 /3. What this means is that 3 is a network host. So we try to expand this. You have a hexadecimal number. It starts with 2. So you expand from 2 to hexadecimal to binary, you don't have a need for binary digits. So that would be 0010. And then all these are zeros. So you have 0000, 0000, 0000. And then this double colon would also represent a string of zeros. So you're going to have zeros up to when you get to the 128th digit. Now /3 means that the first 3 must match. So for a global unicast address, the first 3 binary digits must be 001. That's what it means by 2000 /3. If you expand it to binary, you're going to see that the first 3 digits must be 001. So it could actually be 0010, which would make this 2. It could also be 0011. So if you have an address like 3000::1, for instance, it's also a global unicast address, and shift out inside this range of IP addresses. Next on an IPv6 address we're going to look at is what's called a site local address. And the site local address is also called the unique local address. And basically the site local address is just the equivalence of private IP addresses. Now it really doesn't make any sense to have private IP addresses in IPv6 because we have enough global unicast address to go around, but you know that old habits die hard. So the people that designed the IPv6 addressing just created a scheme for private IP addressing in case anybody wants to use it. And the IP address range is FC00:7. If we expand the first 2 hexadecimal characters, F is 15, so F would be 1111, and C is 12, so that would be 1100. And then of course the other zeros would just be zeros all the way to the 128. If we count the first 7 digits, it would be 1, 2, 3, 4, 5, 6, 7. So what that means is that for site local addresses, they must begin with binary digits 1111, 110. So we don't really care about what all the other 121 bits are. The next kind of unicast IPv6 address we're going to look at is the link local IP address. And the link local IP address is a different kind of unicast IP address because it's only unique on the link. So for instance, if we have a router connected to another router, this interface would have a global unicast IP address or site local IP address. And it'll also have a link local IP address. So pretty much the interface will have 2 IP addresses. But the link local IP address is only valid on this link. So for instance, if you have an Ethernet interface, and you have a host that are connected to an Ethernet interface, so different hosts are connected. As far as a switch is concerned, all these hosts should have unique link local IP addresses. But once it goes out of the link, so once it goes into another network, you can actually have other devices having that same link local IP address, and it really doesn't matter. And by default, once you configure an IPv6 address on a device, it automatically generates its link local IP address. Now you can configure it by yourself if you want, but the link local IP address is automatically generated and uses what is called EUI64. And EUI means Extended Unique Identifier. So what happens is that the device knows that the link local IP address should start with FE80. It's going to say, okay, it's going to be FE80:/64, which means that if we start with FE80 and the rest will be zeros, so what it tries to do is, since it's a /64, it means that the network is 64 and the host is 64. So for the host part, the device would generate it by itself. And the way it does that is that it uses the MAC address. Now, if you remember, the MAC address is a 48-bit address. So for it to get to 64 bits for the host, you need 16 more bits. And the way it does that is just inserts FFFE in the middle of the MAC address. So let's just clear the screen for a second. For instance, let's say we have a router, and this interface has the MAC address 1111.1111.1111. Now, this MAC address is a 48-bit number expressed in hexadecimal. So when the router wants to calculate the link local IP address, what it's going to do is that it's going to insert FFFE in the middle of this MAC address. So the way it's going to do that, it's going to say 1111.11FE111111. So that will become the host part of the link local address. So the full link local address would not now be FE80:1111.11FF:1111:1111. So this is the full link local address. Now for routers that have serial interfaces and Ethernet interfaces, sometimes you would see that the MAC address of the Ethernet interface is also used to generate the link local address for the serial interface, and that's perfectly fine. The link local address is only unique across the link. So those are kind of IP version 6 addresses that we have. Now before we conclude this video on IP version 6 theory, let's just look at how to migrate from IP version 4 to IP version 6. Of all the correct word is how to transition. So as an organization, if you've been running IP version 4 for the past 20 years, and you now need to migrate to IP version 6, you have to have like a transition plan. So that's not really sudden. In the transition phase, what happens is that you can run IP version 4 and IP version 6. So there are different technologies that you can use to do that. And one of them is called dual stack. Dual stack really means you run IP version 4 and IP version 6 at the same device. So for instance, Windows machines from Windows XP, Service Pack 3, I think, has supported IP version 6. So you can actually configure an IP version 6 address on your Windows machine. If you're using Windows 7 or Windows 8, all those operating systems have functionality for IP version 6. Cisco routers to support IP version 6. So you can have a network where you have IP version 4 and IP version 6 running together. So you can have a part of your network. For instance, you can have your router that has an IP version 4 link to another router, but has an IP version 6 link to the internet where your ISP is. It's possible to dual stack and have IP version 4 and IP version 6 running on the same device. And most service providers do that because some customers want to use IP version 4. Some other customers want to use IP version 6. So they have devices that are dual stacked. Next one is tunneling. So it's possible that you have your office. So this is the office. This is like the branch. And then you have another office, which is like the second branch. And they're both running IP version 6, but the service provider on your WAN link provider is running IP version 4. So what happens is that you can have your router here that would tunnel your IP version 6 traffic through an IP version 4 network. And then when it gets to the other end, it's converted back to IP version 6 traffic. So you can tunnel IP version 6 traffic in an IP version 4 network. You can actually do the other way around. The way you tunnel IP version 4 traffic in an IP version 6 network, so you can have what is called a 6 and 4 tunnel or 4 and 6 tunnel. But the bottom line here is that with tunneling, you can have IP version 6 and IP version 4 running together on your network infrastructure. And the last method is NAT. Now remember at the beginning, I mentioned that NAT is one of the reasons why we want IP version 6 because NAT breaks a lot of things. But when we're trying to transition from IP version 4 to IP version 6, in some cases, we have NAT-PT, which is NAT protocol tunneling. And in that case, what you do is that you use NAT to translate from IP version 4 to IP version 6 or vice versa. And with that, you can actually have communication between IP version 4 networks and IP version 6 networks by just having a translation device somewhere in the middle. So we have IP version 4 here and IP version 6 here. So we can have NAT running to translate from IP version 4 to IP version 6 and back. Now, all these three methods, which one do I recommend? It totally depends on the kind of network infrastructure that you have. But if you have your way, dual stack is the most recommended because that way you have an IP version 4 network and an IP version 6 network. They're almost separate, but the rest of them still work. And all these technologies are reliable for you in case you're planning to migrate from IP version 4 to IP version 6. Now, in this video, we've been able to look at what IP version 6 is. We've also been able to look at why we have IP version 6 in networks. We've been able to look at the kinds of IP version 6 IP addressing. We've also been able to look at the kinds of IP version 6 addresses through unicast and multicast. And we looked at things like the global unicast with site local unicast IP addresses and the link local IP addresses. And we wrapped up by looking at the technologies that we can use to transition from IP version 4 to IP version 6. Thank you very much for watching. Hello and welcome to this video on the ICND1 series. In this video, we're going to be configuring IP version 6. So we're going to be looking at this IP version 6 network. So we have two routers, router 1 and router 2. Router 1 is connected to router 2 via a serial link. And IP version 6 network is double colon slash 64. So this is going to be 2013 double colon 1 slash 64. And this would be 2013 double colon 2 slash 64. Now, router 1 has a network behind it, and that's a 2111 network. And that's the 2222 network. So what we're going to do right now is we're going to hop on CLI and first configure the interfaces and see if we can get router 1 to ping router 2 on the serial link. And then we're going to start trying to configure routing, configure our static route, and then OSPF. So let's get started. So we're on 1 right now. And the first thing we want to do when we're going to configure IP version 6 is to turn on IP version 6. So if you remember, the way we turned on IP version routing on the switch, so we're going to go into the router and turn on IP version 6 routing. And the way to do that is to go into the config mode and say IP version 6 unicast routing. So now that we've turned on IP version 6, we can now configure the interfaces. So if we do show IP version 6 interface brief, if you notice, it's the same commands for all the IPs have been changed to IP version 6. So we can see that we have fast Ethernet 0/0, serial 0/0, serial/0/1. Now this serial 0/1 interface connects to router 2. So you go into that interface and say interface serial 0/1. I'm going to give it an IP version 6 address. So we would say IP version 6 address, and it's going to be 2013 double colon 1 slash 64. And then it would bring up and say no shut. If we do a show IPv6 interface brief now, we can see that automatically it has generated its link local address, and the global unicast address is also there. Now let's configure the other interface, fast Ethernet 0/0. So let's say fast Ethernet 0/0 and give it an IP version 6 address. And that would be 2111 double colon 1 slash 64. If we do show IPv6 interface brief again, we get to see the link local address. And if we notice, the link local address is exactly the same, but that doesn't matter because the link local address only has to be unique on the links. So we'll come out. Another command we can use is to show IPv6 interface serial 0/1, and we can see that it's down. The line protocol is also down. We can see that the link local address is set and the IP version 6 global unicast address is set. Now, one thing about serial interfaces that we need to know is that when you're configuring serial interfaces, you always remember to set the clock of the serial interface. So every serial interface has two ends. One is known as a DCE end, which is a data communication equipment, and the other end is known as DTE. So we have serial interface, we have the DCE and the DTE. And you need to set the clock on the DCE end. So we're going to go back to the routers now. So we go back to configure the IP version 6 parameters for R2. We show IPv6 interface here, brief here. Before we configure any IP version 6 parameter, you have to make sure that we turn on IP version 6 routing. So we say conf t and say IPv6 unicast routing. Next thing we're going to do is go into the interface and say interface 01/2, which is the interface that connects to R1. IPv6 address 2013 double colons 2/64. And we would say no shut to bring it up and say interface fast Ethernet 0/0 IPv6 address 2222 double colon /1. Sorry, IPv6 address 2222 double colon 1/64. if we do show IPv6 interface brief, we can see the IPv6 addresses that are configured. We can also see that the interface is still down. The reason it's down is because the clock has not been set yet. So what we're going to do now is to set the clock. And the way to know the DCE is to use the command show control as. So I just can't, so we can use the help. So control as serial 1/2. And we can see here that this is the DCE. So what we're going to see new now is go to the interface and say compt interface serial 1/2. And we're going to say clock set 64000. The command is clock rate, not clock set. Clock set is what you use to set the time on the router. So clock rate 64,000. If we now do show IPv6 interface brief, we can see that it's up. So what we're going to do right now is to try to ping. So we're trying to ping 2013:1. So we say ping IPv6 2013:1. And then we have success. We can reach router 1. Now we can try to ping the fast Ethernet 0/0 interface. That's ping 211:2011:1. We're not going to be able to reach it. And the reason why we can't reach it is because we've not configured the IPv6 route. We're going to go into the config mode and type IP route command, but this time IPv6 route. So it's going to be IPv6 route. We're going to see to get to the 2111 network /64 that we have to go through 2013:1. So what we're saying here is that if we need to get to this network, this /64 network, we go through R1 and type enter. And when we do that, we can now try to ping it. So we ping IPv6 2111:1, and we can reach it. Now, if we go to R1, if we try to ping R2 fast Ethernet 0/0 interface, we won't be able to reach it because we have not configured the static route. So what we're going to do is to configure the static route. So conf t, and we would say IPv6 route 2222:/64. And that's going to go to 2013:2. Oh, it says incomplete command. And the reason why it says incomplete command is because we're supposed to have 2 colons. We had just 1 colon. So now it's going to take the command. So we can try to ping it now. We ping 2222:1. And sure enough, we can reach it. So that's how you configure static routing in IPv6. So before we go into dynamic routing, let's just check our routing table for IPv6. And the way to do that is to show IP route or show IPv6 route. So it will be IPv6 route. And here, it's a little funny because we have how the serial networks and hello networks via serial 0/1. We have a connected route to the 2013 network. So IPv6 not only installs a connected route for each interface, it installs what's called a local route for the particular IP address on the interface. So for instance, for serial 0/1, installs a connected route for the network. And also installs a local route for the particular IP address. And if you notice, it's a /128. And what that means is that it matches a whole IP address. But what you really want to check here is the 2222 network. And here we go. So we can see that there's a static route to the 2222 network, and it goes via router 2. So everything is working fine. So next thing we're going to do is we're going to delete our static routes, and we're going to try to run a routing protocol, which is OSPF. So what we're going to do is we're going to go to configuration mode, or instead, let's show the running config. So we go show running config, and what we're looking for is the IPv6 route. So I'm going to just copy and delete it. So I've copied it and say conf t, and it says no IPv6. So I deleted it. So to remove any command, you just negate that command. and you say no IPv6 route or no IP route and things like that. So we're going to go over to R2. We're going to do the same thing. Conf T, say no IPv6 route 2111:/64 and 2013:1. So if we do show IPv6 route, our static route should be gone, and yes, it's gone. So everything is fine. When we are configuring OSPF for IP version 4, we use the router command. So now what we're going to do is the IPv6 router command. So we say IPv6 router, OSPF, and we would give the process ID as 1. And now it gives an error that OSPF version 3 could not pick your router ID. And the reason why it does that is because OSPF version 3 also uses the same kind of router ID that OSPF version 2 uses, which is an IP version 4 address. Because there is no IP version 4 configured on this router, not a physical address, not a loopback address, it's telling us to enter a router ID manually. So what we're going to do is we're going to configure the router ID and say router ID. I just give it 2.2.2.2. So that's our router ID. And that's all we need to do for the router mode, because unlike OSPF version 2, in OSPF version 3, which is for IP version 6, we don't use the network commands to go into the OSPF process. Instead, we go under the interface to take them into the OSPF process. So it's just going to say exit, and we're going to say interface fast Ethernet 0/0 IPv6 OSPF, the process ID 1, and put it in area 0. And we're going to go under the interface 0/01/22, and that's serial S, and repeat the same command, IPv6 OSPF 1 area 0, and with that OSPF has been configured on R2. So we're going to go to R1 to do the same thing. The first thing we do is configure OSPF, which is IPv6 router OSPF. And we have the same warning. So what we are going to do is configure the router ID and say router ID is 1.1.1.1. And then we're going to come out of there. So we come out of the router process and go into the interface. So interface fast Ethernet 0/0. We say IPv6 OSPF process 1, and it goes into area 0. And then we go into the serial interface to serial 0/1, and we say IPv6 router, IPv6 OSPF 1 area 0. And once we hit enter, we should see the neighbor relationship form. And there we go. You can see that OSPF version 3 adjacency for process 1. And the neighbor 2.2.2, which is a router ID on this serial interface, has come from loading to full. So the neighbor relationship is formed, and it should have learned a route. So now what we're going to do is we're going to go check the routing table. So we'll show IPv6 route, and we can see this OSPF route. And we have learned about the 2.2.2.2 network from the router 2. So if we try to ping now, we should be able to ping 2.2.2.2:1. So we have connectivity, and that shows that OSPF is working well. So from a configuration perspective, the difference between OSPF version 2 for IP version 4 and OSPF version 3, which is used for IP version 6, is that for OSPF version 3, you go into the interface to configure it, but for OSPF version 2, you can configure it with your network command. You can actually go into the interface to configure OSPF version 2 too, but for OSPF version 3, you have to go into the interface. There's no way to configure using network command. So in this video, we started by configuring IP version 6 addresses, and then we moved to IP version 6 static routing, and then finally, we ended up with IP version 6 OSPF configuration. Thank you very much for watching.